Hello everyone. Today we'll talk about race condition, particularly the data races, and how to solve them with Mutex. Let's start with the example program that we had last time. I have a function 1 which counts from 0 downward to -100. And in the main function I create a thread of t1 with function 1, and then I count from 0 upward to 100. And then I wait for t1 to finish. Let me run the program. As you see, the output from this program is pretty messed up. It prints out from main and then nothing, and then from t1 and -59. The reason it happens this way is because we have two threads running, the t1 thread and the main thread, and both threads are racing for the common resource, the cout. A race condition is a condition where the outcome of a program depends on the relative execution order of one or more threads. And typically, race condition is not good for our program, and we should try to avoid it. One way to solve the race condition is using Mutex to synchronize the access of the common resource, in this case cout. First, let me include the header file of Mutex. And then I'll create a Mutex. And then I create a function called shared print, and it takes a string of message, which is like things like the from t1, and then take an integer id. And both t1 thread and the main thread will be calling the shared print instead of using the cout. And same thing for the main thread. I'm missing a D. And inside the shared print function, first of all, it must print the message. So print message and ID and L. But before it prints the message, it will lock the mutex, so that while it's printing the message, other threads will not be able to print the message. And after it's printing, it will unlock the mutex, so that the other thread can lock the mutex and print their message. Now, the access of the common resource cout is synchronized with the mutex mu. It should never happen that two threads are using cout at the same time, as long as they all use shared print function for printing. And now if I run the program again, and as you see, everything is printed out beautifully. So this is how we use a mutex to synchronize the access of common resource like cout among a group of threads. However, there is a problem with this code. What if this line of code throws an exception? Then our mutex mu will end up being locked forever. That is very bad. So it is recommended not to use the mutex's lock and unlock function directly. Instead, we'll use a standard lock guard, standard mutex guard mu. And again, here we are using resource acquisition is initialization technique. Whenever the guard goes out of scope, the mutex mu will always be unlocked, with or without exception. There is another problem with this program. The resource cout is not completely under the protection of the mutex mu. because cout is a global variable, so other thread can still use cout directly without going through the lock. In order to protect the resource completely, a mutex must be bundled together with the resource it is protecting. So a more realistic example is like this. I have a class log file, and log file have a mutex and a of stream f, which will be protected by a mutex. And its constructor opens up a log file, and let's ignore the destructor for now. And it also has a similar shared print function, which use a log guard and a mutex to protect the access of f. And now in the main function, I will need to create a log file, log, and I'll pass the log to the thread T1 by reference. And my function 1 will take a log file reference, and inside T1 it will call log.sharedPrint. And this main function will also call log.sharedPrint. Now the resource f is under the total protection of the mutex. Nobody can access f without going through the lock mechanism. However, you need to maintain this level of protection when you grow the class of log file. There are things that you should never do. For example, you should never return f to the outside world. For example, you should never have a function like this: of stream reference get stream, which will return f. This is a really bad idea, because user will have the opportunity to access f without going through the mutex. And also you should never pass f as argument to user provided function. For example, say we have a function void process f, and it takes a function that takes of stream reference as parameter. And inside this function it will call fun f. Because once you do that, this user-defined function fun can do all the bad things to the resource f. It can print things to f without going through the lock. It can copy f to a global variable so that everybody else can access f freely. It can close f so that nobody else can write to f anymore. So the resource f is out of control. Now let's assume I have used mutex to synchronize the access of my resource, and I have followed all the good design guideline of not leaking the resource to the outside world. Will that guarantee that my program is thread safe? Let's consider a STL container example. Let's consider the class stack. And as we know, the class stack provides, among other APIs, a pop function which pops off the item on top of the stack. And let's use the data type of int. And the top function, which returns the item on top, and it provides some other things. And let's assume the stack use an integer array to store the data, and of course it uses a standard mutex to protect the data. And let's assume both pop and top will access data through the mutex, and the stack doesn't do anything to leak the data to the outside world. And in the function 1, it will take a stack reference data, let's call it st, and in this function 1 it will do integer v equal to st dot top, and then st dot pop to pop off the item, and then call some function that's called process v, so the v will be processed. And the function 1 will be used to launch a bunch of threads, and all the threads will share the same data, stack st. Now the big question is this code thread safe? Let's consider the case that we have two threads, thread A and thread B, and we have a stack that contains 6, 8, 3, 9. Thread A executes first, so it calls the function top and returns the data 6. Then thread B calling the function top and returns 6 also. Then thread A calling pop, so 6 is popped out of the stack. Then thread B calling pop, 8 is popped out of stack. After that, the thread B calling the process function, and then thread A calling the process function. As you see, the number 6 was processed twice, and the number 8 was never processed. Number 8 was lost. So apparently our code is not thread safe. So how did this happen? We have used the mutex to synchronize the access of the data, and we have not leaked our data to the user. Why my code is still not thread safe? In this case, the culprit is actually the interface itself. The interface is designed in such a way that it is inherently not thread safe. The operation of top and pop should not be separated into two operations. They should be combined into one function. So the simple solution is let the pop function return the integer data, and the function 1 will call pop instead of top to get the data, and this line of code can be removed. Now this code is thread safe. But I have to point out that this function may not be exception safe, and that is why the stl stack containers pop function doesn't return a value. But that is not our interest today. So in summary, today we have talked about one particular kind of race condition. It's called data race. And to avoid data race, there are a couple things you can do. 1. Use mutex to synchronize the data access. 2. Never leak a handle of the data to the outside. And 3. Design your interface appropriately. That's all for today. Next time we'll talk about a classic problem that mutex can introduce, which is deadlock. Feel free to subscribe to my channel and check out the other videos I have. Bye bye.